everybody. It's my pleasure to be here today, and thanks a lot for a kind introduction. My name is Jorg, and I will talk about the self-adaptive grasping system today. I'm a third-year PhD student at the University of Pisa. Gualtiero Fantoni is my professor, who will not be here today, and mostly we develop automation solutions. However, in our work, it's very important that our solutions have structural integrity because we deal with many cycles. So we want that the systems withstand the stresses. And today I want to talk about in an industrial project. So we have a strong collaboration with Vitesco Technologies. They have a plant in our region, in Pisa. And Vitesco Technology is one of the key players when it comes to the transformation to electrification in the mobility of the future. And in this plant, they produce electroinjectors, and for electroinjectors, this plant is one of the most advanced plants in the world. However, they were facing some failures in one of the robotic cells, so they asked us to have a look at it. And this cell precisely is handling AdBlue injectors, and the goal of the project was to eliminate defects there and to increase the efficiency of the cell, but also to decrease tool maintenance. My talk today is divided into 4 sections. So first of all, I would like to have a closer look with you at the actual problem we have in the cell, and then we do an evaluation of the developed systems, first with the help of a lab experiment, and then in the system integration of the cell itself. And lastly, I'll summarize my results for you. So what you can see here is the robotic cell. The injectors, they come in a tray of 12 on a conveyor belt. And then they are picked by those pincers, which are mounted on a robot hand, which further on is mounted on a robot arm. They're picked from the tray, and then they're placed in a nest. The nest has 3 brackets, then the nest closes, and the grasping system opens again. And when we first came there, they did that with 100% grasping force of the grasping systems. And they have up to 10,000 repetitions a day of this action. So what is actually happening is that the position in the tray is very inaccurate. They only have one camera on the top. And we have 2 kinds of failures. So the first failure is that the object cannot be grasped properly and it slips out. The second failure is that it is grasped, but it's not centered within the grasping tool, and it cannot be successfully placed in the nest. Further on, we have 43 different variants of this object, and therefore it's very complicated to grasp them all with the same tool. And what you can see here are just 3 different types that are the most common types of the hats where we place the grasping system. So we identified 4 main challenges. So first of all, we want to compensate the misalignment between the grasping system and the actual objects. Then further on in this challenge, we have just a limited contact area we can realize between fingertips and the head of the injector. Plus, as they are packed on a tray, the space between them is very narrow. And then lastly, we want to ensure that we can withstand this high number of repetitions. So we incorporated all these challenges in the design, and then we validated them through a lab experiment, plus to system integration of the developed solution into the robotic cell. And this is what I want to have a look at with you today. Furthermore, we have to mention that a strong requirement by the company was that we only touch the grasping system. So that's the only thing we can change within the whole setup here. In the lab experiment, we mimicked the scenario which we can actually find in the robotic cell. So here we used the Euro 3 instead of the Euro 5 robot, but all the other components are the same. You see our new grasping system mounted on the hand, and then we furthermore have injectors on the tilting table so that we can also introduce an error in the inclination, and we have the nest. We have monitoring with the camera and also laser to ensure that the objects are straight actually when grasped. And the results here, we can look at an offset within the plane, so an XY offset, and we consider it a success when we have 25 repetitions without failure, where we can grasp the object, align it in the system, and successfully place it. And what you can see here, basically with the old system, there was little robustness against misalignment, so we have about 1.5 millimeters where we can successfully grasp, and with the new system we managed to increase this radius significantly, so we can guarantee successful grasping within a radius of 7 millimeters here. This was the type A injector. Then we have the type B injector here, so we could go even further up to 10 for some angles. And then we have here the last injector type C. So for all those three we have a major improvement, and we can guarantee the radius of 7 millimeters. And we also did further tests on an offset in the vertical direction, which were successful. Plus, we tilted the table you saw before up to 9 degrees, and all tests have been successful. And another important fact to be mentioned here is that we managed to decrease the grasping force of the hand to 20%, which is equal to 37 Newton, during all these tests. The situation we found before we did our modifications to the system was that they had 2.5% failures on average every day, which equals 190 failures at 7.6K repetitions a day. And an operator needs about almost half a minute to fix these failures and to reset the cell, which ends up at a downtime of almost an hour and a half. So now in our tests in the robotic cell, we were able to run the cell for several hours without any failures. So we had 0 failures there. However, let's be not too optimistic. So at the moment we aim for a failure rate of 0.025%, which equals a machine downtime of 8 minutes a day. So we recognize that with the old system, the fingertips themselves were very critical because we saw wear there, and it's important that the geometry is very accurate to have this precision in the operation. So the fingertips are from cold work steel, and they were quenched and tempered, and through our modifications we were capable to reduce the surface pressure on the fingertips by the factor of 10. First of all, because we decreased the grasping force by a factor of 5, and then secondly, because we specially designed a new shape of the fingertips so that we could double the contact area. Lastly, through the increase in performance, also we have correct on-axis picking, plus we have reduction of pressures and displacements. So let's summarize this. We were capable to develop and test an adaptive grasping system for AdBlue injectors, and this system is capable to compensate the misalignment between the robotic hand and the actual position of the objects. We significantly increase the expected lifetime of the fingertips, and now the long-term evaluation is still going on in the robotic cell. Thank you very much.
Thank you. So it's open for questions. Yes.
Yes, please.
This increase in pickup accuracy, did you only achieve that by changing the geometry of the hand, or did you also make other modifications?
This is actually the most interesting part. It's a really good question, thank you, of this work. However, as it is an industry project, at the moment I'm not allowed to talk about it.
Next.
Thank you for the presentation. Did you consider changing the coefficient of friction? Because I didn't see you mentioning friction coefficient anywhere. Or, well, if you want to grasp it, you can either increase the normal load, but you also can increase the friction. So did you consider this somewhere in the design of the new?
We considered it. It was one approach. In the end, we didn't go for it because we want the part itself to snap into the crossbar. So there has to be some capability to align, so to slide into the actual position, and therefore we didn't in the end use any kind of rubber coating or something like that, because that would like restrict the actual functionality we want to achieve.
So
Thank you very much.
thank you very much again.